We'll start off with some definitions, pretty basic. I'm going to talk about temperature, dissolved oxygen, and salinity. Temperature is the measure of hotness or coldness in either Fahrenheit or Celsius. All of the graphics you'll see with the example data is going to be in Fahrenheit. Dissolved oxygen, or I'll call it DO, is the amount of oxygen dissolved in water. Higher temperatures leads to a lower capacity for the water to carry DO. And it's also inversely related to temperature. And then salinity is the degree of salt in the water. So variation in temperature is seasonal as air and water temperatures shift. And then, like I've said before, so colder water can actually hold higher amounts of dissolved oxygen than warmer water. DO also changes with organism use and decreases as organisms respirate. And salinity changes occur with freshwater inputs such as precipitation or riverine flow, and also higher temperatures, which can lead to evaporation and increased salinity. So for this project, we collected temperature, DO, and salinity continuously with hobo data loggers, and we measured DO and salinity weekly with a handheld DO monitor and a refractometer. Temperature recommendations for shellfish hatcheries depend on the life stage, but generally range between 75 and 82 degrees Fahrenheit is optimal. For larvae and post-set rearing, we recommend between 68 and 86 degrees. For conditioning, between 64 and 68 degrees is optimal, but for rapid conditioning and pre-spawn priming, 72 to 73 degrees Fahrenheit is optimal. For DO, we recommend values greater than 5 milligrams per liter. And for salinity, the general recommendation is 20 to 35 parts per thousand, but does range with life stage. These three parameters are very important. Temperature and salinity can cause stress, and especially in younger stages, life stages of clams, since their internal temperature and their salinity fluctuates with their environment. And dissolved oxygen is an important parameter to monitor because clams require oxygen for respiration, which they need in order to feed, grow, and reproduce efficiently. So I'll go over some examples of data we've collected and what you can kind of see in the data and what you could kind of tease out of it. So here are two nurseries that use surface water. And we definitely saw a cooler winter in year one, which is the blue solid line. But then as temperatures increase into spring and summer, they tend to coincide for both years. This is a hatchery that uses well water, and something that was interesting for this particular hatchery is that the graphic on the left, which is the tank water, decreases further in temperature in year one, which is the blue line, than the graphic on the right, which is their well reservoir water at the same facility. You can also see that the tank temperature in year two, which is the red dotted line, increases higher than the temperature in the well reservoir water on the right. And this just shows that air temperature probably had a greater impact on the tank water temperature than the well water temperature from the reservoir. And so monitoring reservoir water for temperature alone might not be reliable to reflect the tank temperature. Moving to salinity, this is a nursery that uses surface water. And you can see in year one in blue, the salinity dropped in October, probably due to rainfall or runoff from a hurricane that came through around that time. But just like we saw with temperature, you can notice the spring and the summer temperatures as we go through the season coincide for year one and year two. We generally saw DO above 5 milligrams per liter over the 2 years. This hatchery had a notable dip in both years in late March. And this is an example of how how monitoring this data over multiple years can be helpful in showing patterns. So if you have been looking at your water quality over years and the DO tends to drop at a certain time, or you expect it to drop, you could be prepared to either aerate incoming water or add supplemental aeration to tanks. I'm going to switch now to nutrients, nitrogenous compounds, and give you some definitions. Ammonia is the byproduct of the metabolic process, such as food digestion, decomposition of uneaten food, and organic matter. It's the most toxic of the nitrogenous compounds, and it varies with salinity, pH, and temperature. Nitrite in the middle is formed by the oxidation of wastes containing ammonia, and it's converted by nitrifying bacteria. And then a higher pH can increase the toxicity of nitrite. Nitrate at the bottom is the final product of the conversion in the nitrogen cycle, is also converted by nitrifying bacteria. And both nitrite and nitrate are 10 to 100 times less toxic than ammonia. The equipment we use to measure the nitrogenous compounds are a Hatch spectrophotometer, and we measured those biweekly. We have some recommendations for levels in shellfish hatcheries. For ammonia, we recommend less than 0.1 parts per million. For nitrite, less than 0.2 parts per million should be generally safe. And for nitrate, less than 16 parts per million in salt water should be generally safe. Here is some examples of some of the data we collected over the 2 years for ammonia, also referred to as TAN, total ammonia nitrogen. This is from 2 facilities that use well water, with the first year of data on the left 2 and the second year of data on the right. These ammonia charts have quite a few data points over the threshold of concern, which is indicated by the red line, but the pattern isn't consistent from year 1 and year 2. What we do see are similarities within each year. So in year 1, ammonia has increased a little bit over the year, and then in year 2, it seems to decrease over the season. Moving on to nitrate. I've shown these 2 graphics as an example of what possibly could be an outlier, and then also to make a comment on scale. The first graphic has a value of over 6 milligrams per liter, which is a very high level for nitrite. It might be a questionable value, but that we might expect to be we might expect it to be toxic. And then the next graphic on the right looks fairly similar, but when you look at the scale outlined in that red rectangle, it's an order of magnitude lower than the graph on the right. And all of those values are actually below the threshold of concern, which is 0.2 parts per million. We didn't see any seasonal or geographic patterns in the nitrate. As you can see here, with increases in the nitrate, they don't seem to align with one another across the season. We also didn't see any with source water. So the top 2 graphs are from facilities that use well water, while the bottom 2 facilities use surface water. And there doesn't seem to be a consistency in those nitrite spikes. For nitrite, we didn't have, or for nitrate, we didn't have any values that exceeded the threshold of concern, which is 16 parts per million, but we did have a facility in year 1, which uses well water, that had just 1 data point. And these are bi-weekly measurements. So each of the nitrogenous compounds had 1 data point that was higher than the rest of the season, with only ammonia being above the threshold of concern. And that was consistent across all of the nitrogenous compounds. it could indicate some change, but the next value that we took, the values were back down to what we had seen previously for the rest of the season. There are some really wonderful resources on the website that Natalie's going to talk about later, but I'll highlight just a few, especially this one. It's a chart that goes over all of the water quality parameters and nutrients that I've talked about and much more, and offers definitions, recommendations for values, and then also some solutions if you're having issues. There's also a resource that recommends water quality monitoring equipment for measuring all of these parameters, as well as videos that instruct how to use the equipment that we used in this project. And I can take a couple of questions.
How does TAN differ from ammonium ion? Can you repeat that question for the online participants?
Okay, the question is, how does TAN differ from the ammonium ion? So TAN is going to be your total ammonium nitrate, but I believe it just represents the ammonia, the NH3 really. I'm not sure if our measurements measured the ions alone, but I'm not 100% sure.
I think there's calculations.
Based upon pH.
Most were coming out of the reservoirs. I'm not sure if any came out of any hoses. I know, okay, yeah, yours were all reservoir and mine were all reservoir. Go ahead.
So in the surface water aquaculture setups, wouldn't there be a lot of variability in terms of how much nitrate or would show up in the systems as a result of runoff from potential anthropogenic causes nearby if this is an aquaculture setup near people?
I'd imagine, yeah, I don't think, I haven't looked at it that closely to see if we saw specifically in the surface water. So I'm not sure.
The well water sites, was that?
For the well water sites, was that pumping in just fresh well water and salt was mixed, or was that salt water?
Those are saltwater wells.